All right, we conclude Chapter 5 with Section 5.5, and the topic here is called Integration by Substitution. This is going to be your first integration technique that you're going to see. Hey, we have a whole chapter dedicated to techniques of integration. This is the first one you're going to see. It's going to end up being eventually the friendliest, most basic one. But let's see what it's all about. You know, in a way, integration by substitution or integration using substitution is kind of sort of like a chain rule. So let's review the chain rule of derivatives. So remember, if you're going to differentiate x to the fourth plus 7 cubed, that derivative is 3 times x to the fourth plus 7 squared times 4x cubed. So I'm going to slowly introduce integration using substitution through a couple of examples. So get these examples written in your notes because I'm going to head off to the board. I'm going to introduce what's called U-Substitution on how to attack these. Here I go to the chalkboard. All right, folks, I'm going to run through a couple of examples, part A and B, about this integration using a technique called U-Substitution. But before I do that, I wanted to review something earlier in the semester, earlier in the course. If you're given a function y equals 4x squared plus 8x minus 1, remember that you can find the differential dy. Remember, dy equals f prime of x dx. So we would have dy equals 8x plus 8 dx. But that concept doesn't change if instead of a y, it's called u. The only thing that changes is that the differential wouldn't be dy, it would be du. So here, it would be du equals 8x plus 8 dx. Wanted to review that because that's an important piece on this process called U-Substitution. So we're going to do a couple of examples here. We'll go back to the slides. I'll eventually give you some guidelines for U-Substitution. But this first example, A and B, I'm just trying to ease you into this concept and the process of U-Substitution and how it works. So let's look at part A. Integrate 3x squared times the quantity x cubed plus 5 to the 7th power. Well, folks, without U-Substitution, we'd have to take x cubed plus 5 and multiply it by itself 7 times, and then distribute the 3x squared so we could do term-by-term integration. That would take way too long. But watch. What if I let u equal what's inside the parentheses here? X cubed plus 5. If I do that, I can then determine du. I can get the derivative of u. du is 3x squared dx. Now look at the original integral. X cubed plus 5. I'm going to put u in place of the x cubed plus 5. So that leaves me with a u to the 7th. Alright, now in the original integral, I still have a 3x squared dx. But notice, 3x squared dx is exactly equal to du. So I'm going to substitute du in for the 3x squared dx. That's a pretty friendly integration problem. It's just a straightforward power rule. We know the antiderivative of u to the 7th is 1/8 u to the 8th plus c. Then we resubstitute. U is x cubed plus 5. And how do I know if this is really the correct antiderivative? That's right, differentiate it. So if I differentiate this, I better get the integrand. And when you differentiate it, you're going to have to use the chain rule. And remember, I started off by saying U-substitution is kinda, sorta like a chain rule. You know, I'm saying that because when you check, you would need the chain rule. But we've done part A. Part B. All right, here, I'm going to say, what if we let U equal x squared? I must compute du. Whenever we do a U substitution, once you say what you think U is, you have to compute du. And du is always the derivative of your U statement. So my derivative, du is a 2x dx. Now when I substitute in, the process I got into many years ago was substituting in my U first. So x squared is U, so that would be sine of U. Then I look at what I have left from the original integration problem. Okay, I still have left this 2x dx. It just so happens that my du is equal to the 2x dx, so I substitute du in for 2x dx, and I have a pretty friendly antiderivative to do. The antiderivative of sine, we know the antiderivative, excuse me, the antiderivative of sine is negative cosine of u plus c. Then you resubstitute. So u is x squared, so we have negative cosine x squared plus c. How do I know if that's correct? Differentiate it, and I better get the original integrand back. So let's head back to the slides and see what we're going to do next with this U substitution. All right, folks, we couldn't help but notice that in those two examples I just did on the chalkboard, the substitution worked perfectly. And what I mean by that is when we determined our du, the du was perfectly equal to what was left over in the integrand. Most of the time, it's not going to work perfectly. And we need to do a little bit of massaging. Our next example illustrates what I mean by massaging. So get this example written down because I am heading off to the chalkboard to work through it. Okay, as I just mentioned, the first two examples we looked at, parts A and B, everything worked out perfectly. Our du statement worked out perfectly, and that's normally not going to happen. So I'll show you how you handle that in this example. After this example, when we go back to the slides, I'm going to give you, some tips on U substitution. So this one, the first thing I would do in trying to integrate x cubed square root x to the fourth plus 2 dx is, well, I would rewrite the square root as x to the fourth plus 2 to the 1/2 power. Okay, now I'm going to let u equal the x to the fourth plus 2, kind of like what's inside the parentheses. Once I write down what I'm letting u equal, I must compute du. And du is always the derivative of the u statement. So my du is 4x cubed dx. Alright, now I substitute in, and I always do my u first. So I have x to the fourth plus 2, that's u, so I'd have u to the 1/2. And I look at what I have left over. I have x cubed dx left over. Du does not equal x cubed dx. Du equals 4x cubed dx. So I can't just substitute du in for x cubed dx. But look at my du statement. I mean, it's an equation. I can treat it as an equation. And by treating it as an equation, I'm going to multiply both sides of my du statement by 1/4 to give me 1/4 du is equal to an x cubed dx. Sometimes I call that massaging the du statement. So now I am going to substitute 1/4 du n for the x cubed dx. And as soon as I substitute in the 1/4 du, it's the only time I'll write it like this. Let me pull it up here. I can immediately say, well, let's take that 1/4 and rip it out front. So normally what I'll do from now on is I'll go from here right to here. And I'll just say, hey, let's rip the constant, that 1/4 out front. Now we just get our antiderivative. Remember, leave a little space because we're going to add 1 to the exponent. And here we have to put the reciprocal of the new exponent. 1/4 times 2/3, that's a 1/6. U was x to the 4th plus 2. And we are done. And yes, we can check to make sure that's correct by differentiating it, and we better get the integrand back. But we've done 3 examples now of U-substitution. You might have an idea on what one of my guidelines or one of my tips for what you should let U be by just looking at the 3 examples we've done. But let's head back to the slides and we'll look at the tips or guidelines I have for U-substitution. All right, folks, so we've done 3 examples. I'm going to give you some guidelines now for selecting U. Keep in mind it's guidelines. It doesn't mean it works every single time. That's why it's called guidelines. And you may have noticed maybe what some of these guidelines will be. So in my guidelines, I'm actually going to be foreshadowing some of your future work as well. So here's the guidelines I use for selecting U. Try letting U be the expression that's inside parentheses or under a radical or inside a trig argument. Try letting U be the expression that's in the denominator. You'll see this in Chapter 7. Number 3, try letting U be the expression that's in an exponent position. Okay, you're going to see that also in Chapter 7. And, I have a note here that the last 2 guidelines, it's going to be seen in the next chapter we study. But that's a good, 3 guidelines for selecting U. So let's look at an example. We now have some guidelines. Let's evaluate. Well, there are 4 parts here. Please write down all 4 of them because I'm going to head off to the chalkboard and do all 4. And in particular, attention, Part D has a couple of different ways you could attack it. And we'll discuss that as well. So make sure you write this down, get this in your notes, because I'm heading off to the chalkboard to work through this example. All right, folks, this example we had 4 parts, so 4 integrals. We're going to practice U-substitution. And part A was integrating x squared over the quantity 16 minus x cubed, that quantity squared, dx. So in the guidelines I gave you, I think I mentioned number 2 and number 3. They will be guidelines you'll see primarily starting in the next chapter we do. And hopefully that you saw from the first 3 examples we did that, letting U equal what's inside parentheses could be a wise selection for you. So let's try that here. Let's let U equal what's inside the parentheses. Then we must compute du. Du is the derivative of U, and we get negative 3x squared dx. So I substitute in. So there's my U, so my denominator's U squared. I look at what I still have to take care of in the original problem, and I still have this x squared dx to take care of. My du does not equal x squared dx. My du is equal to negative 3x squared dx. But I just multiply both sides by negative 1/3. That's my massaging here. So I have a negative 1/3 du is x squared dx. So I substitute in a negative 1/3 du. I take the negative 1/3, rip it out front, and I have a very friendly integration problem. I mean, it's friendly if I rewrite it as u to the negative second. Then I use the power rule. Remember, leave a little space here. I add 1 to the exponent, so that gives me u to the negative first. Put the reciprocal of the new exponent in here. The reciprocal of negative 1 is negative 1. Negative 1/3 times negative 1 is positive 1/3. My u was 16 minus x cubed. So the antiderivative is 1/3 quantity 16 minus x cubed to the negative first power plus c. Or if you prefer, you could rewrite this as 1/3 times the quantity 16 minus x cubed plus c. But I ran out of room, so I'm going to stop right there. Part B. Heck, we may not even need U-substitution, but I'll pretend that we do. Let u equal 6x. du is 6dx. Substitute. We have cosine u. The only thing we have left to take care of in the original problem is dx. And by massaging the du statement, we get a 1/6 du is dx. So we're going to substitute 1/6 du in for the dx, rip the 1/6 out front. We have a very, very friendly integral now. The antiderivative of cosine u is sine u. Then you resubstitute, and you get 1/6 sine 6x plus c. So that was pretty friendly. You know, there was a part C and a part D, so let me grab this microfiber cloth, do a little erasing so I can get part C and part D up here on the board. So let's see, in part C we were asked to integrate, ooh, this is a good one, sine cubed x cosine x dx. All right, well, remember, I'm going to write up here as a little reminder. Remember, sine cubed x, that's sine of x quantity cubed. So I would let u equal sine x. Then du is cosine x dx. So I substitute in for my u, and I have a u cubed, and what do I have left? I have left cosine x dx, and hey, how about that? Du equals cosine x dx. So I just substitute du in for cosine x dx. Pretty friendly. Antiderivative is 1/4 u to the 4th. Resubstitute, and we get 1/4 sine to the 4th x plus c. So D, see, part D was integrating sine 2x cosine 2x dx. Okay, I can think of 3 ways to do this one. I'm just now going to talk about, actually I can think of 4 ways to do it, but let's just talk about 2 of them. So I would start, here's how I'd start off. I'm going to do this 2 different ways. So let me start off by saying, I'm going to let u equal sine 2x, then du, well, du is the derivative of this, which would be cosine 2x times 2. Remember the chain rule. So when I substitute in, okay, here's my u, and then I have to still take care of the cosine 2x dx. It looks like 1/2 du is cosine 2x dx. So I'm going to substitute 1/2 du in for the cosine 2x dx, and I'll just rip the 1/2 out front. Very friendly antiderivative, 1/2 u squared. Resubstitute, we get 1/4 sine squared 2x plus c. I'm going to do this a second way. So let me erase part C, and this is the alternative way right now to do part D. And the alternative way is, instead of letting u equal sine 2x, what if we let u equal cosine 2x? Well, then du would be negative sine 2x times 2. So negative 2 sine 2x. And when we substitute in, okay, here's my u. I still have left in the original integrand the sine 2x dx, but negative 1/2 du. That's what sine 2x dx is. So I substitute in negative 1/2 du for the sine 2x dx. I rip the negative 1/2 out front. Antiderivative of u is 1/2 u squared plus c. That gives me a negative 1/4. So we have a negative 1/4. Resubstitute cosine squared 2x plus c. It looks like we got a different answer. But these answers are, I don't want to say it, they're exactly the same. They're mathematically the same. You know, I'm pointing this out because maybe you did the problem like this, and the answer in the back of the book is this. And I don't want you to assume that you are wrong, especially with trig, because with trig, there's usually more than one way to do the problem. So let's say this is the answer in the back of the book, and this is the answer you have. See if you can get your answer to match the back of the book. So what do I mean by that? Well, what I mean by that is, we know an old trig identity. We know that cosine squared x plus sine squared x equals 1. Which means for free, sine squared x equals 1 minus cosine squared x. So if I'm trying to get my answer to match, say, what's in the back of the book, I look at my sine squared 2x and I'd say, hey, I can rewrite sine squared 2x. I can rewrite sine squared 2x as 1 minus cosine squared 2x. So I would do that. Sine squared 2x, 1 minus cosine squared 2x plus c. Distribute the 1/4. And you say, oh, but it's so close to what the answer in the back of the book is. It's exactly the same. Folks, 1/4 is a constant. C is a constant. Combine them. 1/4 plus a constant just gives you a constant. So this is negative 1/4 cosine squared 2x plus a constant, and it matches this one. So you have to be on the lookout on this when we have trigonometric integrals, because there can be more than one way to do the problem, and sometimes the answer in the back of the book did it one way, you did it another, but you can show their equivalent using trig identities. I want you to practice some of these U-substitutions now. We've looked at, 7 of them? We've done 7 examples. So in the section 5.5 exercises, I would like you to try number 19, 23, 33, and 37. So you know the drill. Pause the video, go to section 5.5 exercises, do those 4. Once you're done, restart the video and I'll be here at the board working through them. All right, number 19, integrate 2x squared over the square root of 1 minus 4x cubed dx. So, all right, my first step, rewrite that radical, the square root, as an exponent of 1/2. Then I'd let u equal 1 minus a 4x cubed du. Du is a negative 12x squared dx. So when I substitute in, I do my u first, so I have u to the 1/2. Now I still have a 2x squared dx to take care of. So if I multiply both sides here by a negative 1/6, I get the 2x squared dx. So I substitute negative 1/6 du in for the 2x squared dx. And that's right, I put the negative 1/6 out front. Then I'd rewrite this as u to the negative 1/2. Now I'm ready to do the power rule. So I have a negative 1/6, to leave a little space. Add 1 to the exponent. Put the reciprocal of the new exponent in there. Let's see, negative 1/6 times 2 is negative 1/3. Whoops. Negative 1/3. Substitute my u back in. U was 1 minus a 4x cubed plus c. And if you want, you could have made that, the square root of 1 minus 4x cubed. All right, 23. 23, we're asked to integrate x cubed times the quantity x to the 4th plus 16 to the 6th power. So, yep, I'd let u equal what's in the parentheses, x to the 4th plus 16. du is a 4x cubed dx. So I substitute in. So here's my u. So I have u to the 6th. I still have an x cubed dx to take care of. Well, it looks like a 1/4 du is x cubed dx. So I substitute 1/4 du in for the x cubed dx. Put the 1/4 out front. Now we have a very friendly integral to do. Just the power rule. 1/4, leave a little space, add 1 to the exponent, put the reciprocal of the new exponent in there. 1/4 times 1/7 is 1/28. Resubstitute for the u. And that is it. Oh, we've got 2 more. Bear with me as I erase. There are 2 more I have to do. I momentarily forgot I asked you to do 4 of them from the exercise set. So let's see, number 33. That one's looking a little more intriguing. You have a t cubed sine t to the 4th cosine t to the 4th dt. Okay, I would let u equal the sine of t to the 4th. Then du is the cosine of t to the 4th times, the chain rule, times a 4t cubed dt. So when I substitute in, okay, here's my u. I still have the t cubed cosine t to the 4th dt to take care of. Well, notice, Notice a 1/4 du. It is t cubed cosine t to the 4th dt. So I just simply substitute a 1/4 du in for all that mess. Rip the 1/4 out front. See, the antiderivative of u is a 1/2 u squared. 1/4 times 1/2 is 1/8. My u was sine of t to the 4th squared plus e, or maybe you wrote it as 1/8 sine squared t to the 4th plus c. That's fine. One more here. I asked you also to do number 37. So let's give me some space here. Bear with me as I do a little erasing. So 37. What is this? It's integrating sine x, secant to the 8th dx. Okay, I have to do a little bit of work here with the integrand before I can even think about a U-substitution. Remember, secant is the reciprocal of cosine. So secant to the 8th is equal to 1 over cosine to the 8th. So I can rewrite this integrand as sine x over cosine to the 8th dx. And then it's pretty friendly. I let u equal cosine x. du is negative sine x dx. I substitute in, I do my u first. So I have u to the 8th in the denominator. I still have this sine x dx to take care of, but I mean negative du is equal to a sine x dx. So I substitute negative du in for the sine x dx. And I'll just put the negative 1 out front. Now you know we can rewrite 1 over u to the 8th as u to the negative 8th. Now it's all prepped. It's a very friendly power rule problem. You have negative, let's see, I better put a little space there. Add 1 to the exponent, so that's u to the negative 7th. And here I put the reciprocal of the new exponent, so that's a negative 1 over 7. Negative times negative gives me a positive 1/7. Let's see, u is cosine, so I'd have cosine x to the negative 7th plus c. And if you wanted to, you could write that as 1/7 secant to the 7th x plus c. So hopefully you got those 4. Now we've looked at like 9 examples and ones that you've done as well of, is that right, 9? No, 11. Wow. Hopefully you're getting a handle on the U-substitution. We're going to head back to the slides. At some point we're going to have to talk about how do you do a definite integral with U-substitution. So let's head back to the slides and see what is next. All right, after doing that example, and you did a couple of exercises as well. Hopefully you're getting a handle here on U-substitution. When we have a definite integral and it requires U-substitution, there are going to be 2 ways you can do the problem, which I'll end up calling 2 routes. So here's the first way. Make the U-substitution and leave off the original limits. Those original limits belong to the variable x, not the variable u. So that's why you would leave them off. Integrate, then resubstitute, then you can use the original limits with the fundamental theorem of calculus. Route 2, make the u substitution and change the original limits to u limits. Integrate and immediately use the fundamental theorem of calculus with those u limits that you have. So in our next example, I'm going to actually do both routes to show you how both routes look. And also it will show you that you will get the same answer. Now, folks, in general, I can't tell you, there isn't anyone that can tell you which route is the better route for you. So given a problem, someone can't say, you need to do this problem using Route 2. That's the better route. If you like Route 1, you use Route 1. This is personal. Whichever way you want to go is fine. Now, experience, which means practice, that will help indicate which way to go, which route to use. There are times that I will be adamant, me personally, I want to use Route 1 or I want to use Route 2. But I can't tell you what to do. No one can tell you what to do. So let's look at our first example. We're going to evaluate the following. So there are two definite integrals. Write them down. And as I said, I'm going to, I'll do it both routes so you can see we get the same answer and you can see how to do each route. So write these down because I'm heading off to the chalkboard to do them. All right, just going to see how to attack definite integrals. As I just mentioned on the slides, there are two routes you could go. I cannot tell you which is the best route for you to use. It's personal. So I'll do this first example, part A, showing you the mechanics of both routes. And I took the liberty already to rewrite the square root of 1 minus x squared as 1 minus x squared to the 1/2 power. So no matter which route you go, the first thing you do is figure out your u. Well, u is 1 minus x squared. du is a negative 2x dx. And just kind of looking ahead, after I make my u sub, I'm still going to have an x dx left over. So negative 1/2 du is x dx. So here is route 1. At least what I had on the slides is route 1. Make the u sub. And I said leave off the limits of integration. These limits of integration belong to the variable x. They do not belong to the variable u. So do your u sub, leave off the limits of integration. Get your antiderivative. See, I better put a 2/3 in there. Resubstitute. Now bring back the limits of integration because you have the antiderivative in terms of x. After you resubstitute, bring back the x limits. And, crank this through the fundamental theorem of calculus. So let's see, 1 comes in for x. Well, 1 minus 1 is 0, so fundamental theorem of calculus will give us 0 minus a negative 1/3. 0 goes in for x. Well, that's just a 1. 1 to the 3/2 is 1. So we get a value of 1/3. That's route 1. So let me come over here and do route 2. So route 2 would start the same. Do your u sub, figure out your u, du, and any massaging. So we're going to get to this point right here. So we're at the same point. But in route 2, I said, change these x limits, change them to u limits. And here's how you change them to u limits. This is shorthand for saying x equals 0. So put 0 in here for x. That'll tell you what u is. That's right, u is 1. This is short for x equals 1. So go ahead and put 1 in here for x, and that tells you u is 0. All right, now before I go any further, in case anyone thinks, oh, hey, to change them to u limits, just switch them. That's purely a coincidence on this. purely coincidental. I showed you exactly how to determine what the u limits would be. All right, then we continue. I mean, we're going to get the same antiderivative, negative 1/2 times 2/3 u to the 3/2. But we don't substitute. We don't resubstitute. We have u limits. So we can use the fundamental theorem of calculus. Negative 1/3 u to the 3/2 minus negative 1/3 1 to the 3/2. That's 0 plus 1/3, just 1/3. So of course we're going to get the same answer. So there was a part B. I've shown you both routes. You know, get familiar with both routes, because while I can't say which is better for you, in the future you may look at a problem and say, hey, I'm going to change those limits of integration. Or you may look at a problem and say, there's no way I'm going to change those limits of integration. I can't predict when that's going to happen for you. I mean, it's a very personal thing. So let me put part B up here. So part B was to integrate 0 to 2 x over the square root of 1 plus 2x squared. So I'm going to go ahead and rewrite that with the exponent of 1/2. And here's what I want you to do. I want you to pause the video. I want you to do this example. I don't care which route you use. But pause the video, do this example. When you're done, restart the video. I'll be here at the board to work through it. All right, folks, let's see how you did on part B. All right, I'd let u equal the 1 plus a 2x squared. du is a 4x dx. So when I substitute in, my denominator is u to the 1/2. I still have an x dx to take care of. 1/4 du, that's x dx. So I substitute in a 1/4 du. And now I have to decide which route am I going to go. Am I going to go route 1 or route 2? Leave the limits off or change these x limits to u limits. Remember, it doesn't matter. I'm going to leave the limits off. So I would rewrite this obviously as 1/4 u to the negative 1/2 du. Let me pull this up here. Get my antiderivative. Leave a little space. So power rule, add 1 to the exponent. Put the reciprocal of the new exponent in there. Resubstitute. So I have 1/2 1 plus a 2x squared to the 1/2 power. Bring back the original limits of integration, those x limits. So I have 1/2 times, okay, 2 comes in for x. Let's see, 2 squared is 4. 2 times 4 is 8. 1 plus 8 is 9. 0 squared is 0. 2 times 2 is 2 times 0 is 0. 1 plus 0, that's 1. So this isn't too bad. 9 to the 1/2 power. Square root of 9 is 3. So we get 3/2 minus 1/2. How about that? We got a nice friendly answer. All right, folks, we're going to head back to the slides. We're going to look at something that's very trig specific. So when we go back to the slides, I'm going to review an old identity that you would have seen in trigonometry that I'm calling the power reducing identity. And there are 2 of them. So let's head back to the slides, review power reducing identities and how that can help us in calculus. All right, folks, our final topic here in this section takes us back to some trig. In trig, you would have learned something called the power reducing identities. The power reducing identities are going to be really important now and going forward in the rest of your calculus career. So here are the power reducing identities. Sine squared x equals 1/2 quantity 1 minus cosine 2x. And cosine squared x equals 1/2 times the quantity 1 plus cosine 2x. Really important. Look at this example. Integrate from 0 to pi over 4 sine squared theta d theta. We are going to have to use a power reducing identity to get started here. We will use a power reducing identity on that integrand. So, write all this stuff down, get it in your notes, because I am heading off to the chalkboard to work through this example, and we can see why the power reducing identities are good friends of ours now. All right, we reviewed the power reducing identities, and I wrote them over on the board up in the upper right hand corner. And we're supposed to evaluate this example. Evaluate the integral 0 to pi over 4 sine squared theta d theta. So this is where the power reducing identities come in handy. I can rewrite sine squared theta, thanks to the power reducing identity, as 1/2 1 minus cosine 2 theta d theta. And then I could take the 1/2 and rip it out front. And I should be able to get the antiderivative in one step. The antiderivative of 1, well, that's theta. Antiderivative of cosine is sine. And I have to put a little multiplier of 1/2 in there to neutralize the 2 when we do the chain rule to check it. Evaluate that from 0 to pi over 4. So we have 1/2 times pi over 4 minus 1/2 sine. See, 2 times pi over 4. 2 times pi over 4 is pi over 2. Minus 1/2 times 0 minus 1/2 the sine of 0. I'm going to pull it up here. What's kind of nice here, sine of 0 is 0. So all of this is 0, this product is 0, so this is all I'm left with, which is just 1/2 times pi over 4 minus 1/2. Okay, now what's the sine of pi over 2? That's right, it's 1. So 1/2 times 1. 1/2 times 1 is just 1/2. And see, if I distribute the 1/2 on through, I get pi over 8 minus 1/4. Yeah, I'm not going to go any further. So power reducing identities are going to be with you for the rest of your life in calculus. So get happy with them. Folks, that's it here in section 5.5. So at this time, head off, do the section 5.5 exercises, and thanks for watching.